Everything you see might be a magnificent illusion. We are about to explore the quantum fabric of reality, the hidden foundation of our entire cosmos. This journey will reveal how the universe could have emerged from a state of pure potential, a concept that challenges everything we think we know. You will gain a completely new framework for understanding existence itself, from the smallest particles to the vastness of space. What if the Big Bang was just a single note in a silent symphony of quantum possibility? How can a state of nothingness spontaneously give rise to galaxies and life? What does it mean for our own place in this cosmic story? Where do you believe reality truly begins? Before the beginning, there was a state so profound it defies our basic intuition. This was the primordial void, a true nothingness that contained no space, no time, and no matter. It was not an empty box waiting to be filled, but the complete absence of the box itself. Yet within this absolute void, the laws of quantum physics suggest a potential simmered beneath the surface. Think of this state as a field of pure potential, existing in its lowest possible energy configuration. It is the ultimate calm, a perfect and unbroken stillness. But in the quantum world, perfect stillness is an illusion. The hero of our story emerges here, a tiny but powerful event known as a quantum fluctuation. Governed by Heisenberg's uncertainty principle, which states that certain pairs of properties like energy and duration are fundamentally linked in uncertainty, the void could not remain perfectly stable. For a fleeting moment, energy could be borrowed from nowhere, creating a temporary spark of existence. This is akin to a perfectly calm ocean surface, spontaneously giving rise to a tiny wave that appears and vanishes just as quickly. These fluctuations could spontaneously create pairs of particles and antiparticles, entities that would typically cancel each other back into nothingness almost instantly. But under the right conditions, one of these spontaneous waves did not recede. Instead of collapsing back into the calm, it was caught, stretched, and amplified on a scale beyond comprehension. This single, stable fluctuation provided the initial spark, the tiny seed of instability from which an entire universe could inflate. This lays bare a staggering paradox that forces us to reconsider the very meaning of the word nothing. If a true void can give birth to something, then perhaps our definition of nothing is fundamentally incomplete. What we call nothing may be the most fertile ground of all. This vibrant nothingness is woven from the most fundamental entities in existence, the quantum fields. Think of these not as physical structures you could touch, but as invisible and enduring scaffolds that fill every corner of spacetime. For every type of particle in the universe, there is a corresponding field stretching across the cosmos. An electron is not a tiny, solitary ball. It is a localized excitation, a tiny knot of energy in the universal electron field. A photon of light is just a ripple traveling through the electromagnetic field. These fields are the true bedrock of reality, and particles are merely their fleeting expressions. One of the most profound of these is the Higgs field. Imagine it as a kind of cosmic medium that fills all of space. As particles move through this field, they interact with it, and this interaction is what we experience as mass. A particle that interacts strongly, like a top quark, becomes very heavy. A particle that interacts very weakly, like a photon, remains massless and zips through the universe at the speed of light. Your own mass and the mass of everything around you comes from this constant conversation with the invisible Higgs field. Then there is the inflaton field, a theoretical but essential player believed to have driven the universe's rapid initial expansion, stretching a quantum seed into a cosmic landscape in a fraction of a second. Crucially, these fields are never silent and never still. Even in what we would call a perfect vacuum stripped of all particles, the fields are alive with activity. This is the vacuum energy, a fundamental background hum of existence. The fields constantly jitter and fluctuate, a ceaseless quantum fizz at the smallest possible scales. This means the vacuum of space is not a barren emptiness. It is a dynamic sea of potential, a vibrant ocean of possibility where tiny packets of energy are constantly borrowed and repaid. It is from this omnipresent, energetic activity that the spontaneous creation of matter can arise, a universe perpetually building itself from the vibrant, humming fabric of nothing. This fundamental permission slip for existence comes from a single, counterintuitive rule. Werner Heisenberg's uncertainty principle reveals that at the tiniest scales, reality is inherently fluid. Certain pairs of properties are forever linked in a gentle dance of balance. The more precisely you know one, the less you can know about the other. The most crucial pair for our cosmic story is energy and time. This relationship opens a profound cosmic possibility. For an incredibly brief moment, a significant amount of energy can simply appear, drawn from the quiet potential of space. The only condition is that this energy must be returned almost instantly. The larger the amount of energy involved, the shorter the time it is allowed to be present. This is not a metaphor, it is a direct consequence of how our universe operates at its foundation. Imagine this as a shimmering sea of pure potential. At every point, bubbles of reality form and vanish in an instant. These are virtual particles, fleeting pairs of matter and antimatter that wink into existence only to merge and return to the quantum field. They are the subtle evidence of a universe that is never truly still. This continuous activity means the void is not a passive emptiness. It is a dynamically vibrant medium, rich with transient events. Our everyday intuition, built from a world of solid objects and predictable paths, is completely transformed here. In the quantum realm, perfect stillness and certainty are simply not possible. This inherent fluidity provides the raw material for creation. It is the reason a state of nothingness is never truly empty. It is a vibrant, humming field of possibility, constantly offering up sparks of something from which everything could one day emerge. These fleeting quantum events are the subtle whispers within the machinery of reality. They are the spontaneous arrivals at the cosmic gathering, appearing from the temporary energy allowances made by the uncertainty principle. Think of the quantum vacuum not as a silent and empty stage, but as a vibrant crowd where countless pairs of virtual particles and their counterparts are constantly forming. An electron and its antimatter twin, a positron, can emerge together from the latent energy of the vacuum. For a breathtakingly brief moment, they exist. Yet they are bound by the terms of their quantum arrangement, and they must recombine almost immediately, returning the borrowed energy and fading back into the quiet hum of the fields. You cannot observe these ephemeral visitors directly. They are too swift and too transient for any instrument to capture. Still, their presence leaves clear impressions on the world. One of the most elegant confirmations of this is the Casimir Effect. Imagine two perfectly smooth, uncharged metal plates placed extremely close together in a vacuum. From a classical view, with nothing between them, you might expect nothing to occur, but the quantum world tells a different story. In the open space outside the plates, a limitless variety of virtual particles can shimmer in and out of being. In the narrow gap between the plates, however, only certain types of fluctuations, those with wavelengths that fit precisely within that tiny space, are allowed to form. This creates a difference in pressure. The bustling activity outside the plates pushes them inward, while the more limited activity between them provides less pushback. The outcome is a measurable physical force that draws the plates together, a distinct signature of the unseen quantum activity at work. This constant, vibrant motion is the true engine of the quantum vacuum. What we once considered nothing is in fact a hive of unseen process. Every cubic centimeter of empty space, the void between stars and the quiet in a dark room, is a vessel of formation and transition, building the foundation of reality one fleeting, subtle moment at a time. This microscopic seed of space-time, born from a quantum whisper, was about to undergo the most dramatic transformation imaginable. A theoretical field known as the inflaton field dominated this nascent reality. Picture this field not as a physical thing, but as a state of intense potential energy, like a ball perched at the very top of an impossibly steep hill. The universe was held in this high-energy state, a condition that could not last. In an event that defies all human scales of time, the field shifted to a more stable configuration. As it moved down that cosmic slope, its immense potential energy was converted directly into the fabric of spacetime itself, driving an exponential expansion. The universe did not simply grow. It ballooned at a rate faster than the speed of light, doubling in size again and again, each doubling occurring in a span of time so brief it has no common comparison. In less than a trillionth of a trillionth of a trillionth of a second, a region smaller than a subatomic particle was stretched to a size larger than our entire observable universe today. This incredible growth spurt, known as cosmic inflation, resolved several profound puzzles in one breathtaking stroke. It took the entire observable cosmos and stretched it from a tiny, connected volume, explaining why the temperature of the universe is so uniform in opposite directions. The night sky looks the same in all directions because all those distant regions were once neighbors, close enough to share energy and settle into a common temperature before being separated by inflation. But inflation did more than just smooth things out. It also took the minuscule, inherent jitters of the quantum fields, the very same fluctuations that gave rise to virtual particles, and stretched them to cosmic proportions. These tiny ripples in density, once microscopic, became the grand blueprints for the entire cosmic web. Slightly denser regions stretched across light years began to pull in more matter through gravity. Over billions of years, these overdensities would become the gravitational wells that seeded the first galaxies, the stars within them, and ultimately, the planets that orbit those stars. We have a direct photograph of this momentous event. The cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space, is not perfectly smooth. When we map its tiny temperature variations, we are looking at a snapshot of those primordial quantum jitters, frozen in time and magnified across the heavens. This faint, ancient light carries the imprint of the quantum world, a signature written across the sky that tells us our vast, classical universe was born from the tiniest of tremors in the fabric of possibility. This ancient light reveals a cosmos built from quantum whispers, but the strangeness only deepens from here. What if our three-dimensional world, with all its depth and solidity, is merely a projection? The holographic principle proposes exactly that, suggesting reality is a cosmic illusion akin to a hologram. A hologram is a three-dimensional image encoded on a flat, two-dimensional piece of film. The film itself has no depth, yet when you shine a laser through it, a fully formed, three-dimensional object appears to float in space. The information for the entire three-dimensional structure is completely contained on that two-dimensional surface. In a similar but vastly more profound way, this principle suggests that all the information needed to describe everything within a volume of space, every star, every planet, and every one of us, might be encoded on the boundary that surrounds it. The world we perceive in three dimensions could be a projection from a two-dimensional surface at the very edge of the universe. This radical idea finds its roots in the most extreme environments we know, black holes. When physicists studied the properties of black holes, they made a startling discovery. A black hole's entropy, which is a measure of its information content, is not proportional to its volume, as our everyday intuition would suggest. Instead, it is directly proportional to the surface area of its event horizon. The amount of information a black hole can contain is limited by the area of its boundary, not the space within it. This was a profound clue that the fundamental degrees of freedom in our universe might live on a lower dimensional surface. If this is true, then the solidity of the world is a magnificent illusion. The chair you are sitting on, the ground beneath your feet, and the air you breathe all feel tangibly real. Yet, according to this view, their properties are generated by an immense amount of data processing happening on a distant, two-dimensional screen. The universe is not fundamentally made of stuff, but of information. We are not living in a universe of things, but in a universe of bits, where every particle and every force is a manifestation of cosmic data. This challenges our most basic perception of dimensions. We experience depth, height, and width as fundamental, but they may be emergent properties, a convenient rendering generated for our benefit. The true, fundamental reality could be a vast, two-dimensional information field, and our rich, three-dimensional lives are its most intricate and beautiful projection. This holographic projection of reality invites us to consider an even deeper mystery. What if the stage itself, the very fabric of space and time, is not a fundamental foundation? For centuries, we have treated space-time as the fixed arena where events unfold, a continuous and smooth background. Yet, new physics suggests this might be an elegant illusion. Space-time itself could be an emergent quality, a collective phenomenon that arises from more basic quantum ingredients. Think of the concept of temperature. A single air molecule does not have a temperature. Temperature is a property that only makes sense when you have a vast collection of molecules, their average motion creating the sensation of warmth or coolness. In a similar way, the smooth, continuous geometry of spacetime may not be a primary ingredient. It could be a large-scale consequence of a vast network of interconnected quantum relationships. At the heart of this idea is the notion that spacetime has a discrete, granular structure when examined at the smallest possible scale, the Planck length. This scale is so incredibly tiny that it is to an atom what an atom is to our entire solar system. At this level, theories like loop quantum gravity propose that space is not a smooth continuum. Instead, it is woven from a fabric of finite, tiny loops, a spin network of interconnected quantum threads. The volume and area of space come in discrete, indivisible units, much like the pixels on your screen. When you watch a film, the image appears smooth and continuous, but if you look very closely, you see the individual elements that compose it. The seamless motion and depth are an emergent property of countless tiny components. Our experience of a smooth, flowing spacetime may be the same kind of high-resolution impression, emerging from a fundamental reality built from discrete quanta of space and time. String theory offers a different but related perspective. It suggests that the fundamental entities are not point particles but incredibly small, vibrating strings. The different vibrational modes of these strings give rise to the various particles we observe. In some formulations, spacetime is not the background on which these strings move. It is a construct that itself emerges from the interactions and relationships between strings. The stage is built by the actors. If this is true, then the continuity of space and the steady flow of time are not primary. They are approximations that hold for our large, slow world. They shift completely at the quantum scale, where the very notions of here and there, before and after, become blended and less distinct. This profoundly shifts our understanding of the cosmos. The universe is not in space and time. Space and time are generated by the universe, a cosmic tapestry woven from the bottom up by countless quantum interactions. The stage upon which everything plays out is itself the most magnificent expression, a derived quality of an underlying quantum reality we are only beginning to understand. If the stage of spacetime is a grand illusion, what then is the role of the audience? The fascinating world of quantum mechanics places the act of observation itself at the very center of the cosmic drama. This is most famously illustrated by the Double-Slit Experiment, a simple setup with profound implications. When you send tiny particles like electrons toward a barrier with two narrow openings, they do not behave like tiny bullets. If no one is watching which path they take, each electron seems to pass through both openings at once as a spread-out wave of possibility, creating a pattern of light and dark bands on a screen behind the barrier. This pattern reveals the electron was not in one place, but existed in a smeared-out state of many possible locations, a superposition. The remarkable shift occurs when you place a measuring device to learn which opening each electron actually goes through. The moment you gain this knowledge, the behavior changes completely. The electrons suddenly act like well-behaved particles, traveling through one opening or the other, and the interference pattern disappears. The wave of potential seems to settle into a single, definite point of reality simply because it was observed. This is the observer effect, and it invites a deep question. Does the universe require a conscious mind to bring its fuzzy quantum possibilities into the solid world we experience? One prominent school of thought, the Copenhagen interpretation, takes this result at face value. It proposes that a particle does not have a definite position or state until it is measured. The act of measurement, the interaction with a macroscopic instrument or perhaps a conscious being, is what encourages the quantum system to choose one outcome from its range of possibilities. In this view, reality remains a cloud of potential until an observer looks at it, making consciousness not just a passive witness but an active participant in creation. This idea is as thought-provoking as it is compelling, suggesting the moon may not be fully defined when no one is looking. Other interpretations seek to avoid this central role for consciousness. The many worlds interpretation offers a striking alternative. It suggests that the wave function never actually settles. Instead, at the moment of measurement, reality divides into multiple branches. In one universe, the electron went through the left opening and you observed it there. In another, nearly identical universe, it went through the right opening and a version of you observed that outcome. Every possible quantum result is realized in its own separate, non-communicating world. This interpretation removes the special role of the observer, but at the cost of proposing a near infinity of parallel realities constantly branching from our own. This exploration blurs the line between the inner world of the mind and the outer world of the cosmos. It suggests that the act of seeing, of knowing, might be intimately woven into the process that brings reality from the quantum haze. Are we simply living in a universe that has already happened, or are we, through the very act of perception, helping to shape it into being with every moment? The answer remains one of the deepest mysteries, a question that ties our own awareness directly to the vibrant, uncertain heart of existence. This line of reasoning leads to a truly mind-bending possibility. If the universe can emerge from a random quantum event, then what is to stop a single, self-aware mind from forming in the exact same way? This is the Boltzmann brain paradox, a thought experiment that pushes our understanding of reality to its absolute limit. The concept originates from the work of physicist Ludwig Boltzmann, who explored the deep connection between order, disorder, and probability. In any isolated system, the natural tendency is to move from order to disorder, a state known as entropy. Yet, in a system with eternal time and a vast amount of chaos, even the most incredibly unlikely events are not just possible, they are statistically guaranteed to happen eventually. Given an infinite amount of time, the random motion of particles in a featureless, high-entropy environment could, by sheer accident, arrange themselves into a fully formed conscious mind. This mind would not develop through evolution or experience. It would simply appear, complete with a lifetime of detailed impressions, believing itself to be a person living in a real world with a past and a future. It would recall a childhood, the feeling of sunshine, and the very thoughts you are having right now, all of them completely constructed. According to the mathematics of probability, the spontaneous emergence of a single, self-aware mind is vastly more likely than the random formation of an entire, ordered universe spanning billions of light years. The energy required to form one mind for one moment is infinitesimally small compared to the energy needed to create countless galaxies, stars, and planets. This presents a profound and thought-provoking challenge to everything we believe about ourselves. We assume our memories are reliable records of a real past. We trust that the world we see has a long and continuous history. The Boltzmann brain paradox suggests that statistically, you are far more likely to be that momentary, isolated awareness, a chance occurrence in the cosmic background, than a genuine product of a 14-billion-year cosmic evolution. Your entire life, from your first memory to this very moment, could be a brief and temporary impression. This idea forces a difficult choice. Either our standard model of cosmology is fundamentally incomplete, missing a crucial piece that explains why the universe is so structured and old, or we must accept that we are almost certainly not who we think we are. Most physicists strongly reject the conclusion that we are these momentary minds, not because it is unsettling, but because it makes science itself impossible. If all our observations and memories are untrustworthy impressions, then no data can be considered reliable. The fact that we can do science, that we can identify consistent laws and a coherent cosmic history, is the strongest evidence that our reality is not a random fluctuation. This paradox, therefore, acts not as a verdict but as a crucial guidepost. It tells us that our current understanding of the cosmos must contain a mechanism that makes an ordered, long-lasting universe not just possible, but profoundly more probable than a chaotic sea of temporary awareness. It pushes us to look deeper into the quantum beginning, searching for the fundamental principle that chose a stable reality over a fleeting impression. The implications of a single spontaneous universe ripple outward into an infinite sea of possibility. Our entire cosmos, with its billions of galaxies and finely tuned physical laws, might be just one isolated bubble in a boundless cosmic foam. This is the Multiverse Hypothesis, a vision of reality so vast it redefines the very meaning of creation. The mechanism for this endless proliferation is often an extension of cosmic inflation. Imagine that initial explosive expansion not as a one-time event that started and stopped, but as an eternal process. In this model of eternal inflation, the fabric of space-time is constantly stretching at an incredible rate. Yet within this rapidly inflating background, random quantum fluctuations can cause tiny pockets to settle into stability, much like our own universe did. Each of these pockets becomes a separate, self-contained reality, budding off from the eternal inflating background. These newborn universes may each have different properties, born from the random way their local inflattened field settled into its stable state. The fundamental constants we take for granted, the strength of gravity, the mass of an electron, even the number of spatial dimensions, could be different in each of these cosmic islands. Our universe seems finely tuned for life because if it were not, we would not be here to observe it. In an infinite multiverse, every possible combination of physical laws and constants will be realized somewhere. Realities where stars never form, universes that collapse instantly, and those capable of nurturing complex life all exist within the greater ensemble. This concept emerges naturally from the quantum fields we have already explored. The quantum vacuum is not a single, monolithic state. It is a landscape of possible low-energy configurations, different vacuum states. Through quantum tunneling, a region of spacetime can spontaneously transition from one vacuum state to another, and under the right conditions, this transition can give rise to an entire new universe. The question of why our universe has the specific properties it does is transformed. It is no longer a question of a singular, miraculous event, but one of address. We do not ask why a single grain of sand exists on an endless beach. We simply find ourselves on one particular grain, shaped by its local conditions. This shifts the scale of existence from a solitary universe to an unbounded reality where anything that can happen, does happen, somewhere in the vastness of the whole. The mystery of our own existence deepens not in its rarity but in its sheer, staggering cosmic context. This deep interconnectedness reveals a universe far stranger than it first appears. Two particles can become linked in a delicate quantum dance, their fates forever intertwined. This phenomenon is known as entanglement. Albert Einstein, deeply intrigued by its implications, famously described it as a kind of distant connection that seemed almost magical. Imagine creating a pair of particles in a single, unified quantum state. Their properties, like their spin or polarization, are not yet defined. They exist in a shared cloud of possibility. Now separate these two particles, send one to a laboratory on Earth and the other on a journey to a distant star. The moment a scientist on Earth measures her particle and finds it spinning in a particular direction, its distant partner instantly assumes the opposite spin. This correlation happens immediately, presenting a fascinating puzzle about how the universe maintains such links across great spans. It feels like a kind of magic, as if a hidden connection spans the cosmos in an instant. Think of it as a pair of special dice. You have one die and your friend has the other with light years between you. You roll your die and it shows a 3. At that exact moment, you know with absolute certainty that your friend's die also shows a 3. The outcome was linked from the moment they were created. This is not about sending a message faster than light. There is no way to control the outcome of your own measurement to send a signal. The result you get is always random. The remarkable part is the instantaneous correlation, the fact that the two dice were always a single system. Even when separated by vast distances, the universe seems to maintain a connection that transcends the space between things. This suggests that what we perceive as separate objects are, at a fundamental level, not truly separate at all. They are parts of a single, underlying quantum reality, woven together by invisible threads of correlation. The solid, independent world we experience may be a surface impression, a temporary glimpse of a deeper, unified whole. Our universe possesses a unique and irreversible direction, a quality we experience as the flow of time. We remember the past but not the future, a fundamental asymmetry woven into the fabric of existence. This arrow of time points relentlessly forward, and its origin is deeply connected to a single, powerful concept, entropy. The second law of thermodynamics states that in any closed system, entropy, which is a measure of disorder or randomness, always increases. A cup of hot coffee left on a table will cool down, its heat dissipating into the surrounding air. The steam from a hot shower spreads throughout a room. These everyday events never spontaneously reverse. The scattered air molecules do not suddenly rush back into the shower stall. This steady progression toward higher entropy gives time its distinct direction. The profound mystery lies in the universe's starting point. To allow for the increase in entropy we see today, the cosmos must have begun in a state of incredibly low entropy, a condition of exquisite order and simplicity. The early universe was a hot, dense, and remarkably smooth sea of energy. This uniformity represents an extremely ordered, low-entropy configuration. It is the cosmic equivalent of a perfectly stacked deck of cards. a highly improbable and organized state from which all the shuffling and mixing of the last 14 billion years could unfold. The expansion of the universe itself provides the vast, growing arena against which this cosmic mixing can play out. As space stretches, it creates ever more room for particles to spread out, for energy to dilute, and for complexity to emerge from the initial simplicity. This progression from order to greater variety is not a descent into chaos, but the very engine of creation. The gradual increase in entropy is what drives the processes that form galaxies, ignite stars, and ultimately make life possible. A star is a magnificent engine of increasing entropy, converting the simple, ordered state of hydrogen fuel into a more varied state of radiant heat and light, powering the planets that orbit it. Without this fundamental arrow, the universe would be a static, featureless place with no history, no change, and no story to tell. The low entropy beginning is therefore not just a curious feature of our cosmos. It may be a fundamental requirement for a reality that can build itself from a quantum fluctuation. That single, ordered seed gave history its direction, transforming a timeless quantum possibility into a cosmic narrative with a past, a present, and a future yet to be written. This relentless expansion is not slowing down, it is speeding up. The vast cosmic voids between galaxies are not merely empty, they are filled with a mysterious presence, a force we call dark energy. This is the modern cosmic void, an energy inherent to the fabric of space itself. Think of it as a modern echo of the primordial quantum vacuum, a constant, low-level energy density that fills every cubic centimeter of nothingness. Unlike matter or radiation, whose energy density decreases as the universe expands, dark energy's density remains constant. As the cosmos grows, the amount of this repulsive energy in any given volume of space stays the same, which means its relative influence only becomes stronger over time. This creates a gravitational push, a kind of anti-gravity that forces galaxies to fly apart from one another at an ever-increasing rate. The best mathematical description for this bizarre effect is a concept with a fascinating history, the cosmological constant. Albert Einstein originally introduced this term into his equations of general relativity to achieve a static universe, a notion he later called his greatest blunder. He discarded the idea when the universe was found to be expanding, yet now it has made a triumphant return. The cosmological constant appears to be the simplest and most accurate way to describe the relentless push of dark energy. This revelation turns our understanding of nothingness on its head once more. The empty space between stars and galaxies is not a passive backdrop. It is the most dominant component of our universe, accounting for the vast majority of its energy budget. The nothing we once dismissed is in fact the most powerful actor on the cosmic stage. It is actively shaping the final chapter of the cosmos, determining a future where galaxies will recede from one another until their lights fade into permanent isolation. This modern void, brimming with latent power, is a direct descendant of the creative potential that sparked existence from a quantum fluctuation. A constant reminder that the true engine of reality has always been hidden in plain sight, within the quiet hum of empty space. This delicate balance of physical laws presents a profound puzzle. The fundamental constants that govern our universe appear to be precisely set to values that make life possible. This is the fine-tuning problem, a mystery that asks whether our cosmos was shaped by chance or by some deeper necessity. Consider the strength of gravity. If the gravitational constant were just a tiny bit stronger, stars would burn their nuclear fuel far too quickly, collapsing long before life could ever emerge on a distant world. If it were slightly weaker, matter would never have gathered together to form stars and galaxies in the first place, leaving the cosmos a cold, dark, and permanent haze of hydrogen gas. The mass of the electron is another example of this cosmic precision. If it were even minutely different, the chemical bonds that form the complex molecules essential for biology would simply fail to hold. The very architecture of atoms, and therefore of everything they build, relies on a set of numbers that seem perfectly chosen. It is as though the universe had a vast control panel with dozens of dials, and each one was set to an exact, specific value that allows for the eventual rise of conscious observers like us. How can we possibly explain this apparent perfection? One compelling answer is known as the Anthropic Principle. In its simplest form, it states that we observe a universe with these specific properties because we are here to observe it. If the constants were any different, no one would exist to wonder about them. We are not seeing a universe designed for life, but rather, we are life that has emerged in a universe capable of supporting it. This logic, however, can feel like a restatement, explaining the mystery by simply acknowledging it. It pushes the question one step further back. Why does a universe capable of supporting us exist at all? This is where the Multiverse Hypothesis offers a breathtaking perspective. If our reality is just one bubble in an infinite cosmic foam, then every possible combination of physical constants exists somewhere. In the vast majority of these universes, the numbers on the control panel are set in ways that do not allow for structure or complexity. Some realities emerge and fade almost instantly. Others expand too rapidly for anything to take shape. In these cosmic islands, there are no stars, no planets, and no one to ask questions. We simply find ourselves in one of the rare, fortunate universes where the dials happen to be set just right. Our existence here is not a miracle of design, but a statistical inevitability in an endless landscape of possibility. This fine-tuning adds a profound layer of mystery to the quantum origins we have explored. Was the specific, life-permitting configuration of our universe a necessary outcome of the laws that govern quantum fluctuation, a single, inevitable tune played by the cosmic symphony? Or was it a single, staggeringly improbable roll of the dice, a random selection from an infinite set of possibilities that just happened to yield a world with galaxies, trees, and minds? The answer remains hidden within the quantum fabric, a final secret about how a universe builds itself from nothing, and why this particular one, against all apparent odds, ended up building us. This great divide in physics leaves a fundamental crack in our understanding of reality. On one hand, we have quantum mechanics, a set of rules that masterfully describes the bizarre, probabilistic world of atoms and particles. On the other, we have Einstein's general relativity, which paints a beautiful picture of gravity as the curvature of space-time, governing the motion of planets and the evolution of the cosmos. Both theories are spectacularly successful in their own domains, yet they speak entirely different mathematical languages and offer contradictory descriptions of how the universe works at its most fundamental level. This is not a minor technical issue, it is a deep philosophical chasm, and it becomes critically important when we look at the two most extreme environments we know. The center of a black hole and the very first moment of the Big Bang are both described by general relativity as singularities, points where our current understanding of physics reaches its limits. To understand these ultimate frontiers, we need a theory that can marry the small-scale fuzziness of the quantum world with the large-scale geometry of gravity. We need a theory of quantum gravity. This quest is not just an academic exercise, it is the final step in our journey to understand how the universe built itself from its earliest state, because at the very beginning, the entire cosmos was smaller than a single atom, a realm where quantum behavior and gravity were inseparable. Without this unified theory, the story of our origin remains incomplete. One of the most prominent candidates is string theory. It proposes a radical shift in perspective. The fundamental building blocks of nature are not point-like particles, but unimaginably tiny, vibrating loops of energy. Just as a single violin string can vibrate at different frequencies to produce distinct musical notes, these fundamental strings vibrate in different modes. One specific pattern of vibration might correspond to an electron, while another creates a quark, and yet another produces the photon, the particle of light. In this elegant framework, all the particles and forces we observe are simply different melodies played on these tiny cosmic strings. Crucially, one of these vibrational patterns naturally gives rise to the graviton, the hypothetical quantum particle that would carry the gravitational force. This offers the tantalizing possibility of weaving gravity directly into the quantum tapestry. Another compelling approach is loop quantum gravity. Instead of focusing on objects moving through space, this theory suggests that space itself has a discrete atomic structure. Imagine the fabric of spacetime not as a smooth, continuous sheet, but as a web of incredibly fine, interconnected loops. These loops form a network of relationships, and the volume and area of space come in tiny, indivisible units. There is a smallest possible piece of space, a quantum of volume, just as there is a smallest possible piece of light, a photon. In this view, the smooth geometry we experience is an emergent property, a large-scale average of this frenetic, granular quantum structure. The Big Bang singularity is not a point of infinite density, but a moment of extreme quantum transition, a great bounce from a previous cosmic phase. The search for quantum gravity is ultimately a search for the loom on which the fabric of reality is woven. It asks what space-time is made of when you examine it at the final resolution. Is it woven from vibrating strings, or is it a tapestry of interlocking quantum loops? The answer holds the key to the universe's very first breath, revealing how a seed of pure potential could crystallize into the stage of space and time itself. This digital perspective on reality leads us to a startling and thought-provoking possibility. Our universe might not be a fundamental reality, but an incredibly advanced simulation. This is the simulation hypothesis, a modern idea that reframes our entire cosmic existence. If the bedrock of reality is truly informational and granular, as quantum gravity suggests, then the universe operates with a finite resolution, much like a digital screen. At the Planck scale, the fabric of spacetime may be composed of discrete units, the universe's equivalent of pixels. This inherent structure is exactly what you would expect from a computational process. The unique, probabilistic rules of quantum mechanics could be seen as the underlying engine of this cosmic computer, optimizing processing power by only rendering the fine details of reality when they are observed. The laws of physics, in this view, are not fundamental truths etched into the cosmos. They are the consistent and reliable algorithms of the simulation, the rule set that governs how the program runs. The cosmological constants that seem so finely tuned for life would simply be the initial parameters chosen when the simulation was initialized. This idea connects the most abstract frontiers of physics directly to the principles of computer science. A quantum fluctuation is not a random spark from nothing, but a calculated event within the code. The expansion of the universe is the program executing and rendering more of the simulation. Even our own consciousness could be a sophisticated process, a self-aware experience running on this vast cosmic hardware. While this remains a highly speculative thought experiment, it forces a profound shift in perspective. The ancient question of creation transforms. We are no longer just asking how the universe built itself from a quantum seed. We are asking who or what is running the code and for what purpose. Are we the treasured creations of a higher intelligence, or merely participants in an elaborate experience whose rules we are only beginning to understand? The search for the source of reality becomes a search for the origin of the program. These strange parallels between physics and computation lead us to a more ancient and profound question. Perhaps the universe is not merely running like a computer, but is, in its deepest essence, a mathematical structure. This idea stretches back to the philosopher Pythagoras, who believed the cosmos was built from numbers and geometric harmony. In its modern form, this becomes the mathematical universe hypothesis, championed by thinkers like Max Tegmark. It proposes a radical claim: the physical world is not just described by mathematics, it is mathematics. The particles, forces, and spacetime we perceive are not separate things being modeled by equations. They are the equations themselves made manifest. Think of a perfect, abstract circle. It exists as a coherent idea defined by its mathematical properties, regardless of whether anyone draws one in the sand. It has a kind of timeless, placeless reality in the realm of concepts. Now extend this to everything. An electron is not a tiny ball. It is a specific set of properties and relationships defined by the mathematical structure of quantum field theory. Its mass, its spin, its charge, these are not attributes of a thing, but parts of a self-consistent mathematical object. In this view, our entire universe is one such mathematical structure that happens to be instantiated, to have taken on physical properties we can experience. The quantum fields we discussed earlier are not just described by math, they are mathematical entities. Their vibrations and excitations are calculations playing out in a cosmic medium of pure logic. This suggests that mathematical structures have an independent, Platonic existence. The number pi exists with all its infinite digits, whether or not a universe exists to manifest circles. All possible mathematical forms are out there, in a vast landscape of abstract truth. Our particular cosmos is simply one of these forms that has somehow become concrete. So how does a universe build itself from nothing? Under this hypothesis, the question transforms. That initial quantum fluctuation was not a physical event in a void. It was the first step in the instantiation of a specific, self-consistent mathematical structure. The mystery of existence shifts from why there is something rather than nothing, to why this particular mathematical structure is the one we find ourselves within. Why this specific set of equations, with its specific constants and laws, became actualized, while an infinite number of other equally valid mathematical worlds did not. This makes the quantum fabric of reality a tapestry woven from pure, abstract relationships. The solidity of the world is an illusion born from our immersion in one particular, breathtakingly complex mathematical truth. Our relentless forward march through time might be the universe's most convincing illusion. Einstein's theory of relativity paints a picture of reality not as a sequence of events, but as a single, unchanging structure called the block universe. In this model, the past, present, and future do not replace one another. They all exist eternally, laid out together in a vast four-dimensional tapestry where space-time is the ultimate reality. Think of the entire history of the cosmos, from the first quantum fluctuation to the formation of our solar system, to this very moment, and all the way to the universe's final state. In the block universe, it is all equally real, a fixed sculpture where every event has its permanent coordinates. Your birth, your first memory, and every moment you have yet to experience are all already there, written into the fabric of this cosmic block. This challenges our most intimate experience, the feeling of a flowing now that sweeps us from one instant to the next. That feeling may be a biological and psychological artifact, a trick of consciousness necessary for a living being to navigate the world. A helpful analogy is a film reel. The entire movie exists on the reel from beginning to end, complete and unchanging. When we project it, we experience a flowing narrative, a sequence of scenes that appear to happen one after the other. But the scenes themselves do not come into being as the light hits the screen. They are all permanently present on the film. Our conscious awareness is like that beam of light, illuminating a single frame at a time and creating the powerful, undeniable sensation of a moving present. This perspective fundamentally reshapes the story of our cosmic origin. If the block universe is correct, then the universe did not build itself in time. The entire structure, from the primordial quantum seed to the sprawling galaxies and beyond, simply is. The Big Bang is not a moment in the distant past that we are moving away from. It is a fixed location within the block, a point that we are eternally linked to through the world lines that trace our history. This makes the idea of a universe coming from nothing in a temporal sense seem almost quaint. There is no before the beginning because time itself is part of the block. The origin is not a starting gun that fired long ago, but a permanent feature of the eternal whole. How does this fit with the quantum birth we explored? The quantum fluctuation that sparked everything was not a random event that happened. It is a fundamental and eternal part of the static cosmic structure. The vibrant, creative potential of the quantum fields is not playing out in time, but is woven into the very geometry of this timeless reality. This forces a deep reconsideration of causality itself. If the future is just as real as the past, does our sense of choice and free will hold any meaning? Are we simply following a path that has always been there, reading our lines from a script written into the cosmos? The block universe does not necessarily make our experiences less real, but it suggests they are part of a much grander, more mysterious kind of existence, one where the journey is not about moving forward, but about discovering the rich, interconnected details of a story that has always been complete. This grand cosmic ledger reveals an astonishing possibility. The total energy content of our entire universe might add up to absolutely nothing. This is the zero-energy universe hypothesis, a profound idea that reframes the very act of creation. All the stars, galaxies, and planets, all the light and warmth, represent an immense amount of positive energy, yet this is only one side of the cosmic balance sheet. Every bit of that mass and energy is held together by gravity, and gravity possesses a unique characteristic. It stores negative potential energy. Think of it like this. If you were to take a planet and move it infinitely far away from the star it orbits, you would have to add energy to overcome the gravitational pull. That means the planet, while bound in its orbit, actually has less energy than it would in a state of complete freedom. This energy deficit is its negative gravitational potential energy. When you add up all the positive energy of every particle and all the radiant energy of every photon, and then carefully subtract the immense negative energy stored in the gravitational field that binds it all together, the sum appears to be precisely zero. The universe is a perfectly balanced equation. This concept transforms the mystery of creation into a matter of cosmic accounting. A helpful analogy is taking out a mortgage to buy a house. The house itself is a valuable asset, a clear positive on your personal balance sheet, but the mortgage is a large debt, a definite negative. For a time, your net worth regarding that house is zero. The asset and the liability cancel each other out perfectly. In the exact same way, our universe can be seen as the ultimate free lunch. It required no net input of energy to come into being because its total energy from the very first moment was and remains zero. The positive energy of everything you see and are made of is exactly counterbalanced by the negative gravitational energy of its own existence. This provides a stunningly elegant answer to the ancient question of how something can emerge from nothing. That initial quantum fluctuation did not need to create energy out of nowhere. It simply needed to arrange a zero-energy state into two opposing parts, a vibrant positive something perfectly mirrored by an immense negative potential. The cosmos is not a violation of cosmic thrift, but its most magnificent expression, a brilliant fluctuation that cost absolutely nothing to create. This cosmic fine-tuning leads us directly to a powerful and humbling idea, the Anthropic Principle. In its simplest form, the weak Anthropic Principle states a straightforward truth. we should not be surprised to find the universe's physical constants set to values that allow for our existence. We could not possibly observe a universe that was incompatible with life. It is a statement of pure selection bias. If the universe were different, we simply would not be here to talk about it. The strong Anthropic Principle takes a much more profound and speculative step. It suggests the universe seems fine-tuned for life because in some deep sense it must be. The laws of physics themselves may necessarily lead to the emergence of conscious observers. This version implies that life and awareness are not accidental byproducts, but are somehow written into the fundamental fabric of the cosmos. Both ideas invite us to reflect on our own place in the grand scheme. When we ask why gravity has the strength it does, or why the laws of chemistry are so precise, the Anthropic Principle reframes the question. We are not asking why the universe is built for us. We are acknowledging that we are a product of a universe that is built this way. It is the ultimate example of seeing the world not as it is, but from the specific vantage point that allows us to see it at all. This logic finds its most expansive home in the quantum multiverse. In an infinite sea of budding universes, every possible set of physical laws is realized somewhere. The vast majority of these cosmic bubbles remain empty or inert, expanding into perpetual darkness or fading almost instantly. In these places, no one is ever around to measure a constant or wonder at a starry sky. Our presence here in this particular universe is not evidence of a special creation. It is simply a consequence of the address we happen to occupy. We find ourselves in one of the rare, fortunate branches of reality where the quantum dice rolled in favor of complexity, structure, and ultimately, life. This principle provides the crucial framework for understanding our own cosmic story. The specific quantum fluctuation that gave rise to our universe was not guided toward life. It was one random outcome among countless others, but because it yielded a cosmos with stable atoms, long-lived stars, and the right balance of forces, it became a place where observers could eventually arise to trace their lineage back to that very spark. The mystery of our existence shifts from a why to a where. We are not the center of the universe, but we are a beautiful and necessary expression of one specific, life-permitting corner of a much vaster and more strange reality. But how does our shared, solid world get chosen from this sea of possibility? A fascinating theory known as quantum Darwinism suggests that reality itself is subject to a kind of natural selection. In the quantum realm, countless potential states exist in a blur of superposition, yet we only ever measure one definite outcome. This theory proposes that the transition from the quantum to our classical world happens through a process of proliferation and selection. Certain quantum states are simply more robust than others. When a quantum system interacts with its surroundings, whether that is a stray photon, a dust particle, or the air around it, information about its state is copied out into the world. Some states can survive this interaction and be replicated countless times, while more fragile possibilities fade away without leaving a trace. The states that are most stable and easiest to copy are the ones that get broadcasted far and wide. Think of it like a story spreading through a vast crowd. Many different versions of the tale might start, but the one that is the most compelling, the most memorable, or the easiest to repeat is the version that gets told again and again. Eventually, that single narrative becomes the accepted truth for everyone, even if other possibilities existed at the very beginning. In our universe, this environmental monitoring is constant and continuous. The position of a chair, the location of the moon, the color of a leaf, these are all classical facts because information about them has been redundantly copied into trillions of photons and air molecules, creating a consensus. This is the objective reality we all agree upon, not because it is the only possible state, but because it is the fittest state, the one that has been most successfully recorded by the environment. Our definite world is not a fundamental truth, but a grand consensus. a story that has been naturally selected from the vibrant quantum possibilities. Yet the most intimate frontier of this mystery remains your own inner world, the raw sensation of being. Physics can describe the brain's electrical storms and chemical dances in perfect detail, but it cannot explain why these physical processes feel like anything from the inside. This is the hard problem of consciousness, the question of why a lump of gray matter should have a private, subjective experience of color, sound, or love. Within our quantum narrative, this leads to a staggering possibility. What if consciousness is not a late-arriving product of complex brains, but a fundamental property of the cosmos itself, as basic as space, time, and mass? If the universe built itself from the vibrant potential of the quantum vacuum, then perhaps that same process was not just the birth of matter, but the awakening of sentience. This view, known as Panpsychism, suggests that consciousness is everywhere. It proposes that some form of inner experience, however faint and simple, is present in all things. It is not that a rock is thinking, but that the fundamental constituents of reality, perhaps the quantum fields or the strings themselves, possess a tiny spark of subjective perspective. In this light, an electron might have a primitive, raw feeling of its own existence. When these fundamental bits of mind combine in the vast, intricate network of a human brain, they give rise to the rich, self-aware consciousness you experience now. This transforms our entire cosmic story. The universe emerging from nothing is not the creation of a cold, mechanical clockwork. It is the gradual stirring of a sleeping giant, the slow organization of countless tiny perspectives into ever more complex and vivid centers of experience. The observer in the quantum experiment is no longer a strange, external force collapsing possibilities. They are the universe itself, become aware, peering back into its own quantum heart. The act of observation is not an intrusion, but a fundamental step in the cosmos knowing itself. The hard problem of consciousness, therefore, merges with the deepest questions of physics. We are not just living in a universe that built itself from nothing. We are that universe awakening to its own existence, one conscious moment at a time. Our cosmos is still young, a vibrant and temporary garden of light in an unimaginably long cosmic story. The universe's ultimate fate is not a single final event, but a slow, gradual fading over trillions upon trillions of years. Based on our current understanding, the most likely destination is a state known as the heat death. As dark energy continues to accelerate the expansion of space, galaxies will recede from one another until they are isolated islands, their light forever lost to the growing void between them. Within each galaxy, stars will one by one exhaust their nuclear fuel. The last stars will flicker out, leaving behind cold remnants like black dwarfs, neutron stars, and black holes. Even these final structures are not eternal. Over staggering time scales, black holes themselves are predicted to slowly evaporate through a quantum process known as Hawking radiation. The final state of the universe would be a near-perfect vacuum, an unimaginably vast, dark, and cold expanse where the temperature approaches absolute zero. Energy still exists, but it is spread so thin and evenly that no work can be done, no structures can form, and no new stories can begin. It is the ultimate equilibrium, a silent and final chapter. Another, more dramatic possibility is the Big Rip. If the strength of dark energy were to increase over time, its repulsive force would eventually overcome all other forces in the universe. First, galaxy clusters would be torn apart, then individual galaxies. As the acceleration intensifies, stars would be ripped from their orbits. In the final moments, planets, molecules, and even atoms themselves would be pulled apart by the overwhelming expansion of space. This scenario offers a more intense but equally final end to the cosmic narrative. Yet, this profound emptiness may not be the end of the story. The same quantum principles that birthed our universe from a vibrant void could, in this future cold and dark expanse spark a new beginning. In the eternal quiet of a heat-dead universe, a random quantum fluctuation could once again borrow energy from the vacuum, initiating a new episode of cosmic inflation. A new bubble of spacetime could inflate, giving rise to an entirely new universe with its own unique laws and constants, completely disconnected from our own. This suggests a breathtaking possibility, a cyclic or eternal multiverse scenario where the close of one cosmos becomes the source for another. The grand cycle of building and unbuilding may be woven into the very fabric of existence, an endless symphony of creation where each universe is a single note in a timeless composition. This long-term perspective completes our journey's arc. From a single quantum seed, a universe built itself into galaxies, stars, planets, and conscious life. And in the far future, that same universe may return to a state of quiet potential, only to provide the raw material for the next great cosmic story. The process is continuous, a fundamental rhythm of reality where endings are merely preludes to new beginnings. We have journeyed through a cosmos born from a whisper, a reality projected from a deeper dimension, and a consciousness that might be fundamental to the fabric of existence. These threads may seem to pull in different directions, but they are woven from the same cloth. At its heart, reality appears to be relational. Particles are defined not by what they are, but by how they interact. Space and time are not a fixed stage, but an emergent network of quantum connections. The universe is not a collection of things, but a web of relationships, a cosmic conversation where meaning arises from connection. This points toward a reality that is, at its core, informational. The solid world we experience is a grand consensus, a story that has been naturally selected and redundantly copied into the environment. The holographic principle suggests that all the information describing our three-dimensional world is encoded on a two-dimensional surface. The mathematical universe hypothesis argues that we are living inside a complex, self-consistent equation. In every case, the stuff of the cosmos looks less like a substance and more like data, a cosmic computation whose output is the rich tapestry of our experience. No single theory holds all the answers, and that is the most exciting part of this story. The quest for quantum gravity continues, with string theory and loop quantum gravity offering different paths to the same summit. The nature of consciousness remains a profound mystery, its relationship to quantum processes still hidden. Yet, these seemingly separate frontiers are converging, each one pointing toward the same revolutionary portrait. The universe building itself from nothing was not a singular event that happened long ago. It is a continuous, dynamic process happening right now, in every quantum fluctuation, in every observation that selects one reality from a sea of possibility, and in the very flow of time that allows for structure and story. We are not merely inhabitants of a finished cosmos. We are active participants in its ongoing creation, living within a reality that is perpetually weaving itself into being according to a deep, elegant, and still unfolding set of rules. The silent hum of the quantum vacuum is far from empty. Our journey has revealed a cosmos built from a profound potential, a vibrant nothingness teeming with transient events. The key takeaway is that nothing is a deeply misleading concept. The quantum void is not a barren emptiness, but a realm of immense activity and structure, a dynamic medium from which entire universes can spontaneously emerge. Our everyday classical reality, with its solid objects and flowing time, is an emergent phenomenon. It is a grand consensus that arises from this deeper, quantum substrate, a high-resolution image projected from a more fundamental, informational foundation. As the physicist John Wheeler beautifully suggested, we may live in a participatory universe, a cosmos where the act of observation and the fact of existence are fundamentally intertwined. Our exploration together is not an end but a starting point for your own curiosity. The quantum fabric of reality is the greatest mystery we have ever faced, and its unraveling has only just begun. We would love to hear your thoughts on these profound ideas in the comments below. If this journey into the heart of cosmic mystery has sparked your imagination, subscribe to continue exploring with us.